Consider three vectors in R3, 1, 1, 2, 2, 2, 5, and 3, 3, 8. At first glance, they look independent. None of them is a scalar multiple of another. Now let's stack them as columns of a 3 by 3 matrix A. Look carefully at the rows. Row 1 reads 1, 2, 3. Row 2 also reads 1, 2, 3. The rows are identical. Having two identical rows forces the determinant to equal 0. The matrix is singular, and therefore the columns must be linearly dependent. The rows just reveal the fact about the columns. Understanding this deep link requires the four fundamental subspaces that every matrix naturally carries. One matrix, four worlds. That example hints at deep structure. Let's define it precisely. Take any m by n matrix A, where m is the number of rows and n is the number of columns. We write the entries as A sub ij, arranged in a rectangular array. Now, perform row reduction on this matrix. The number of pivots you obtain is called the rank, which we denote by R. The rank always satisfies an important inequality. R is at most the minimum of m and n. This makes sense because you can have at most one pivot per row and at most one pivot per column, so the number of pivots can never exceed either m or n. Here is the key insight. The four fundamental subspaces of A and all of their dimensions are completely governed by just three numbers, m, n, and r. Let's look at the first two of the four fundamental subspaces. First up is the column space of A, written C of A. To build it, take all linear combinations of the columns of A. Since each column has m entries, these combinations are vectors in Rm. The dimension of the column space equals R, the rank, because the R pivot columns form a basis for this space. Now the second subspace, the null space of A, written n of A. This is the set of all vectors. X satisfying A times X equals the 0 vector. Since X has n components, the null space lives in Rn. Its dimension is n minus R. Why? Because when you perform row reduction, you get n minus R free variables, and each free variable gives rise to exactly one basis vector for the null space. This fact is known as the rank nullity theorem. The dimension of the column space plus the dimension of the null space equals n, the number of columns. Now let's look at the third subspace, the row space, written C of A transpose. This is the column space of A transpose, which equivalently means all linear combinations of the rows of A. Each row of A has n entries, so the row space lives in Rn. Its dimension is also R, the rank of the matrix. Next, the fourth and final subspace, the left null space, written n of A transpose. This consists of all vectors, y satisfying A transpose times y equals the 0 vector. Since A transpose is an m by m matrix, the vector y must live in Rm, so the left null space is a subspace of Rm. Its dimension is m minus R. But why is it called the left null space? Here's the neat trick. Start with A transpose times y equals 0. Now transpose both sides. The left side becomes y transpose times A, and the right side stays 0. Notice that the vector y transpose now sits on the left side of A. That's exactly where the name left null space comes from. Here's the complete picture in one table. We have four subspaces, and for each one, we list where it lives and what its dimension is. First, the column space of A lives in Rm and has dimension R. Second, the null space of A lives in Rn and has dimension n minus R. Third, the row space, which is the column space of A transpose, lives in Rn and has dimension R. Fourth, the left null space, which is the null space of A transpose, lives in Rm and has dimension m minus R. Now notice how these pair up beautifully. In Rn, the row space has dimension R and the null space has dimension n minus R. Together, R plus n minus R equals n. They account for all dimensions of Rn. In Rm, the column space has dimension R and the left null space has dimension m minus R. Again, R plus m minus R equals m. The subspaces in each ambient space perfectly use up every available dimension. Let's return to our 3 by 3 matrix. The rows of A are 1, 2, 3, 1, 2, 3, and 2, 5, 8. First, subtract row 1 from row 2 to get 0, 0, 0. Next, subtract 2 times row 1 from row 3 to get 0, 1, 2. Now swap rows 2 and 3. The echelon form U has rows 1, 2, 3, 0, 1, 2, and 0, 0, 0. The pivots are in columns 1 and 2, so the rank R equals 2. Column 3 is a free column. Now we solve Ux equals 0. Since column 3 is free, set x3 equal to 1. From row 2, x2 plus 2 equals 0, so x2 equals negative 2. From row 1, x1 plus 2, x2 plus 3, x3 equals 0. Substituting, we get x1 minus 4 plus 3 equals 0, which simplifies to x1 minus 1 equals 0, so x1 equals 1. Therefore, the null space basis vector is 1, negative 2, 1. This confirms all 4 fundamental subspace dimensions. The column space C of A has dimension 2. Columns 1 and 2 of the original matrix form a basis. The null space N of A has dimension 1, spanned by the vector 1, negative 2, 1. That vector encodes the column dependency. Let's verify. 1 times column 1, which is 1, 1, 2, minus 2 times column 2, which is 2, 2, 5, plus 1 times column 3, which is 3, 3, 8, equals the 0 vector. Checking the first component, 1 minus 4 plus 3 equals 0. Second component, 1 minus 4 plus 3 equals 0. Third component, 2 minus 10 plus 8 equals 0. Confirmed. The row space C of A transpose has dimension 2, and the left null space N of A transpose has dimension 1. Now, why does row rank always equal column rank? Row reduction changes individual rows but preserves the row space. The echelon form U has R non-zero rows spanning that row space, so the row rank is R. The same pivots identify R independent columns in the original matrix spanning the column space, so the column rank is also R. One set of pivots, one rank R, governs both spaces. Here's a common mistake, confusing which subspace lives where. The column space and left null space live in Rm. That's the output space where A times X lands. The row space and null space live in Rn. That's the input space where X lives. Think of it this way. The matrix A maps from the input space Rn on the left to the output space Rm on the right. The row space and the null space split up the input side, while the column space and the left null space split up the output side. In our 3 by 3 example, all 4 subspaces happen to live in R3, so the distinction doesn't seem to matter. But for a non-square matrix, these ambient spaces have different dimensions entirely. For instance, a 4 by 7 matrix maps from R7 to R4. The row space and the null space live in R7 on the input side, while the column space and the left null space live in R4 on the output side. Keeping track of which side each subspace belongs to is essential for avoiding confusion. Step back and see the full architecture. Every matrix A maps from an input space, Rn, to an output space, Rm. Inside Rn, the row space and the null space divide the entire space into 2 complementary pieces. Their dimensions R and M minus R sum to N. Inside Rm, the column space and left null space do the same. Their dimensions R and M minus R sum to M. This structure is universal. It holds for every matrix regardless of size or entries. One round of row reduction reveals the rank R, and that single number determines the dimension of all 4 subspaces. There's more to come. These complementary pairs are actually orthogonal complements. The row space and the null space are perpendicular. The column space and left null space are perpendicular. That's the next chapter. For now, remember, one number, the rank, reveals the hidden architecture of any matrix.